So this is question number 9. And the amount of energy is just the work done in spinning up the blades, which will be the change in kinetic energy of the blades. So they're starting from rest to a speed of 200 or 600. Those are going to have to be in radians per second. So, do the conversion, get them from RPM to radians per second. But all you're doing is plugging in 1/2 I omega squared. Now, they do tell you that the blades are a rectangle. So, or they're a long bar. So you're given the shape of the blades straight away. That is 1, right? There's a total of 3 of them, and they're spun about their center. So all right, close enough. So this is the length of the blade, and it's spun about the center. They give you the numbers. I don't care about the numbers. We'll plug them in at the end. A single blade is a bar spun about its center, 1/12 ml squared. By looking at all the writing, I'm a little concerned because this is not much. How many blades are there? So 3 times 1/12 ml squared equals 1/4 ml squared. And that's it. So this is going to be 1/2 times 1/4 ml squared times omega squared. Plug in your numbers. That's the amount of work necessary to spin it up. Do you need me to do the arithmetic? Okay, so that's enough for that? I don't care. It's your time. I can. All right. Make sure you convert to radians per second. Now, the next part asks for the net torque necessary for the blades to come to rest from the highest speed. And torque's about acceleration. So to find the net torque, you have, I think, 2 alternatives. You can find the work done, but that's not going to be enough because it's not going to give you the acceleration. Acceleration has something to do with time. But they tell you it takes 5 minutes for them to come to rest. This seems like the job of a motion equation. The initial speed is 600 rotations per minute. The final speed is 0, and it takes 5 minutes to come to rest. You put everything in radians and seconds, you'll probably get the acceleration. Right? 600 RPM is about 63 radians per second. And 5 minutes is 300 seconds. It's not much here. We already know I. It's 1/4 ml squared. So the net torque, which will be the torque from friction and air resistance, required to bring the blades to rest. Just plug all that in. That's it. That's question number 9. It's not particularly interesting. Number 9 is a multiple choice question, right? Where some of the answers I don't convert correctly. Some of the answers I use 1 bar, not 3 bars, right? That's the kind of multiple choice I would expect. All right. Is that good enough? Okay. Unless there's some reason to believe we're all the way at the threshold, then the amount of static friction available is probably less than the maximum. And for rolling, we don't know where we are on that spectrum. So it is unlikely that we'll be able to use the coefficient in our answer because we don't know where we are on this inequality. However, we do know quite a bit of other things about this problem that should be able to be sufficient for us to figure it out. For example, if I start the object on the ramp and release it, I know from past experience that there's got to be 3 forces that act on the object. Right? We've done this before. So I'm thinking weight downwards. None of this goes away just because it's rolling. Normal force upwards. And the one that might be the more difficult for you to spot, there has to be a frictional force acting on it. But the direction of friction might be confusing for you. But is this object speeding up or slowing down? So if I kind of consider the fact that there's, more than one point in time for this object, right? So maybe right here, I've just released it and that's at rest. But right here, it's begun to roll. And so it has both a angular and a linear velocity. And after a little bit longer, it has an even larger angular and linear velocity. Friction can only act in one of two directions. Friction either acts this way or it acts this way. Which of those two is going to cause it to increase its angular speed? Up the ramp or down the ramp? Will this cause an object to spin what appears to be clockwise? I just don't think so. So in dealing with the direction of friction, friction has to be up. So that's my frictional force. I'm going to make down the ramp positive, just like I would for anything else that's sliding down a ramp. Net force in the x direction is going to equal ma. I think this thing accelerates down the ramp. I'm going to make down the ramp the x direction. So I'm doing all the stuff we used to do for force. Because you guys, are familiar with it. That's the x direction. That's the y direction. So in the x direction, I'm thinking mg sine theta minus friction equals ma. Things that slide down a ramp will slide. Things that roll down a ramp will be slower than things that slide without friction. Not surprised. Now, there's also net force in the y direction equals 0, but I think this is less useful. It's going to give us that normal force equals mg cosine theta. But like I said, unlikely to be able to use that. So, I'll hold on to that just in case. But these are the ways in which we've dealt with. Now, we're asked to find the size of the frictional force. And right now, we could do so. Except which of those letters is not allowed to be in our answer? M can be in our answer, right? G can be in our answer. Theta can be in our answer. Which one can't be? A can't be in our answer. So we need more information. This is a unit on torque, right? So perhaps we should stop and take a look at what's happening with torque. And this shouldn't be a surprise. We know from just looking at it, right? From actually putting something that rolls on the table and seeing that the ring rolls slower than the disc, that somehow the moment of inertia has to get worked into this problem somewhere. This seems like the right place for that, doesn't it? So I think here's where we're going to see the moment of inertia get worked into the problem. You have a choice to make. One of the choices is more physicsy than the other, but one of them is easier than the other. You have to choose a pivot point for this problem. And I think students They probably like the center to be the pivot point. Like the friction's causing it to spin about its center. That's actually not the pivot point. The pivot point is here because this point's not moving. With respect to the ground, right, that point's stuck. But I'll be honest, this pivot point is much harder to use than this pivot point. So we're going to use the easy pivot point. Now, this is the only time besides statics where you could do this. Every other time, you have to use the pivot point they tell you to use. But in this pivot point, we can use the center. So we're going to use the center. It's much easier. Part of the reason it's easier is because the weight acts at the center, so it doesn't cause a torque. And the normal force points through the center, so it doesn't cause a torque. The only thing that causes a torque is the frictional force. That's worth writing down. I know all of you are just standing there wanting me to do the whole problem, but you understand that the only way you're going to catch on to any of this is if you do something. I'd encourage you to write it down. Why isn't the weight causing a torque? Why isn't the normal force causing a torque? These sound like questions I would ask on a test. So the weight doesn't cause a torque because it acts at the pivot point. So the torque arm length is 0. Just a small reminder that torque is R times F times the sine of the angle. So the weight acts right at the pivot point, right here. So R is 0 for the weight. The normal force, it points right towards the center. So the angle between this direction and this direction is 0 or 180. It doesn't matter because sine of 0 or 180 is still 0. So there's no torque from that force. The normal force can't cause a torque because it points through the pivot point. So the only thing that can cause a torque is friction. Friction is acting a distance r away from the pivot point. Friction is tangent to the disk, so the angle is 90 degrees. So the torque from friction is going to be R times F times the sine of 90 degrees. That's the torque from friction. Now, my understanding is that we were doing this for the disk, right? Because that's what I drew, but you're supposed to do this for the disk and the ring. So I'm going to choose the disk because that's the one that we have here. And that's important because I now have to use net torque equals I alpha. So net torque is R times F. And I'm going to, sine of 90 is 1, so I'm just going to not write it down. But I is the moment of inertia of a disk. So 1/2 mr squared times alpha. Any question about that yet? Okay. Is the object rolling? I mean, it's kind of in the problem, right? It's rolling down the ramp. If it's rolling, then A equals alpha times R. Putting everything in terms of A is probably helpful since we want to eliminate A. So I'm going to put everything in terms of A. So that means RF equals 1/2 mr squared times A over R. Now, I've got a bunch of you that don't see this. You just don't have the mental chops, or it's too early in the morning, or you're only paying partial attention because you're trying to get your A push done or something. But the R's all cancel here. Every time we've done this and converted to one of those variables, the R's have tried to cancel. You should be getting to the point where you try stuff like that. And in this case, they do cancel. I can cancel one of them right now. And then I can divide both sides by r and get rid of the other one. So F equals 1/2 ma. Well, what now, Mr. Shelton? Well, we're trying to find friction, but I can't have A in my answer. Well, what did I do? I used Newton's laws. Newton's laws generated 3 relationships, apparently. 2 for force and 1 for torque. 2 of those have all the same variables, friction and acceleration in them. I might be able to eliminate A. In fact, that's exactly what I'm going to do. Remember, all Newton's laws can do is produce a relationship that you might be able to use to solve for acceleration or force. I say it over and over again. Same thing's going to apply here. Torque is just another way of using force. So I'm going to say that 2 times the friction is equal to ma. Because this equals ma. Seems like this would be an easy substitution, right? Did you think to do this? I don't know. Sometimes you guys think of stuff like this. Sometimes you don't. But I think of this. This will make it easy. So I'm going to bring these things together right down here. mg sine theta minus friction equals 2f. Solve for f. mg sine theta equals 3f. So f equals 1/3 mg sine theta. That's a good one. That's good. We can do that. I like that one, okay. By the way, the only thing that makes this problem different if it's a ring is that this, which is the moment of inertia, won't be 1/2 mr squared. This will be mr squared. Now, you could redo the whole problem, but do you realize that if that's mr squared, then this just becomes F equals ma? So this is for the ring. It's already solved for ma, so if this is the disk, then I can put the ring right next to it. mg sine theta minus f equals f. mg sine theta equals 2f. So f equals 1/2 mg sine theta. Which one experienced more friction, the ring or the disk? The ring experiences more friction. Which one takes longer to get to the bottom, the ring or the disk? The ring does, yeah. Of course, it's experiencing more friction. It's going to take longer to get to the bottom. It's experiencing more friction. You can see it right there. Why is it experiencing more friction? It's harder to turn. If it's harder to turn, it's going to take more friction to turn it. Friction is on a sliding scale, remember. You have not an unlimited amount, but you have a scale. Friction will increase to meet demand. A ring is more difficult to turn. Look, justify your reason using nothing but, words without using any math. I'm giving you the things to say. I do it all the time, but you don't write it down. But this is the good stuff here, right? We're able to show quite clearly that if you increase the inertia, it takes more friction to get something to turn. It's clear. I mean, it's not clear maybe to all of you, but it should be clear to a few of you that the math is pretty straightforward. When you increase the inertia, that frictional force has to increase because the thing is harder to turn. Oh, well, I tried. So if you use the pivot point here, although you'll have to use the parallel axis theorem, you also eliminate friction as one of the things that can be in your equation. Yeah. So the torque becomes the weight because it's causing a torque. That's now the actual torque.
So that's why it's the same thing.
It's the same thing, but it doesn't give you, it's not easy. I will say, since it's just a soccer ball and it's a hollow sphere, you're just running the numbers the same way as before. They give you an angle, they give you the mass of the ball, they give you its radius, all that kind of stuff. I'm not sure how much of it's going to be necessary. It depends on what you want. They want the acceleration and they want the friction, both. You'll need to pick one to solve for at a time. It doesn't make a difference to me which one you do that with, but right here, if I just put the ball here, then I'm looking to start my problem kind of right there. Again, I think you should do the entire problem over again if you want to understand this. But I have a limited amount of time in class, so I'm not going to. I'll have RF equals, instead of 1/2, I'll have 2/3 mr squared times alpha. And then plug in A over R if it's rolling. And they say it's rolling. So F is going to equal, what, 2/3 MA. So if I want the frictional force, MA is going to be 3/2 F. And now mg sine theta minus F equals 3/2 F. So you can find the frictional force first, then go back and find A. We good? More to this problem? All right. That's it. Shoot the ball. My pulley being held up by some two blocks. Cable. We good? All right. Newton's law problem. So let's hit the high points here. Would you agree that if this weight goes down, this weight goes up? If the cable that's used on the pulley doesn't slip, then would you also agree that the pulley has to rotate? Pulley has inertia, so it's going to take an unbalanced torque to cause the pulley to rotate. I'm going to choose all those arrows as the positive direction for this problem. Everybody good with that? All right, so that's positive, positive, positive. I think that there are two forces acting on the 2m mass. Two mg downwards and a upwards tension that has to be less than the weight, so that block can accelerate downwards. The other box has to experience a force that is less, mg, right? Half of 2 mg. But the upwards tension has to be greater than mg. It's made it a little bit greater, because something else is occurring to me that I'm going to have to take into account. These two tensions can't be the same. The only way to turn the pulley is if there's an unbalanced torque acting on the pulley. Looking at the forces acting on the pulley, I suspect there is a force downwards on this side of the pulley and a force downwards on this side of the pulley. these two forces can't be the same size or the pulley won't turn. The torque has to be unbalanced. That's the whole idea. If the pulley has weight, it has inertia. And the only way we can cause the pulley to turn is if the net torque is unbalanced. There are only two torques that act on the pulley to cause it to turn. I think T2 and T1 have to be different sizes, with T2 being greater than T1. There are other forces acting on the pulley, don't forget them. The pulley is experiencing weight, 3 mg, and some kind of upward force that's keeping the whole thing in place, something from the stand or the mount or something. Net force on the pulley is 0. Right, the pulley stays in place, but net torque on the pulley isn't. I see two torques acting on the pulley. Let's deal with the pulley first. I see a radius here and a right angle again because it's a pulley. So I think R T2 sine 90 degrees is one of the torques acting on the pulley. I'm skipping a step. I'm not writing out the whole torque. I mean, we did that once today, but... Right? That's how we get a torque. But T1 is also causing a torque in the opposite direction. It is a torque arm of R as well. So minus R T1 sine 90 degrees. And that equals I alpha. Now I'm going to set that aside. We have two other masses we have to deal with. In a force problem, we break our problem up into individual masses, and we deal with the forces that act on each mass. So the mass over here on the left, I've got T1 minus mg equals ma. Right? It's one-dimensional, and I'm choosing upwards to be positive. Any question about that? On the right side, 2mg minus T2 equals 2ma. Right? Net force equals, don't forget, its mass is 2m. All right, when you reach this point, remember, all Newton's laws can do for you is generate a series of relationships that could be used to solve for an individual force or the acceleration. I have my individual relationships. Now, it's how I use them that matters. The first thing I'm going to notice is that this is in terms of alpha. This is in terms of A. I got to pick one. Is it clear to you that the motion of the system is all connected together?
Yes.
And the string doesn't slip, so A equals alpha times R, where R represents the radius of the pulley. This seems like a good substitution to make. So RT2 minus RT1 equals... I left parentheses there because this is a disk, right? Moment of inertia of a disk. 1/2 3m r squared. Don't forget the mass of the pulley is 3m. So I've got to put its mass in there for the mass of the object. You'll forget to do that. And they're counting on it. So don't. 1/2 mr squared, m is the mass of the object. So if the mass is 3m, put in 3m. All right, it's a whole lot. It looks kind of messy, so let's make it less messy. T1 minus mg equals ma. 2mg minus T2 equals 2ma. RT2 minus RT1 equals equals 1/2 3m r squared a over r. There. I'm just putting it all together in one place. I see that we could factor out an r on the left. You can also see I can cancel out an r on the right. Looks like I can get rid of the r's everywhere. But after looking at the faces and people in first period, I'm doing this just because I not because I want to, clearly, but because I feel like I have to. One-step simplification, right? Remove one of the r's, show that I can divide both sides by r here, because I have a lot of people who don't understand how that works and think if they see r in one term, it's okay, but it has to be in all the terms. So now I can get T2 minus T1 equals 3/2 MA. We all good? Everybody follow? Three equations. I think we can eliminate all the tensions. I see a positive 2t and a negative 2t, a positive t1 and a negative t1. If we add these together, looks like all the tensions cancel. You guys see that okay? So left side, 2mg minus mg. Right side, m plus 2m plus 3/2 m, all times a. I'm writing it like this because I do it all the time, don't I? This side, the net force. I hung two weights, one on either side of the pulley. They're battling it out to see which one wins. Looks like the 2mg is going to win. Inertia now includes three objects, because three objects are moving. Both masses and the pulley, which has mass. But notice, even though the pulley has mass 3m, only half of its inertia actually matters. Do you see that? Because it's rotating, so we treat the inertia differently. Now, if it were a ring, I'd have a different thing there. You understand that too, right? So different objects will behave differently. If I have a ring, I think this number will be bigger. More inertia, the system will be slower. Either way, I can use this to find the acceleration. And you should. The math isn't hard. The left side is mg. The right side is 1 plus 2 plus 3/2. That's 3 plus 3/2 or 9/2. MA. So cancel the m's, and A equals 2/9 G. Good one. Easy. Super straightforward. Now you can go back and find T1 and T2 if you want. Or if it's asked of you in the problem. As logical it is methodical. I'm going through the same set of steps, right? The same set of 4 steps as before. Trying to be slow, methodical, diplomatic. That's what we get. You kind of know how I feel about stuff like this. I'm just going to say the whole thing is length L. This distance, 30 centimeters, right? So, I guess I could do it as a meter stick. It'll be easier for you guys. So, there's a torque here. If you're trying to do does it ask for acceleration and then ask for velocity? Or does it just ask for velocity and it swings down? Okay, I'd be able to find the acceleration if I were you guys. It's just setting this equal to I alpha. And there's one torque, and that's based on this being 0.3 meters and this being mg. So I'm not asking a lot here to expect you that you can do this. You release it, you could find the acceleration. But you do need the moment of inertia. And we don't have the moment of inertia. The moment of inertia we'll have to get from the parallel axis theorem. Be careful. They tell us that the pivot was shifted from the end a distance 20 centimeters. But the parallel axis theorem is referenced from the center of mass of the object. So this is going to be 1/12 ml squared plus m times 0.3 squared. And L in this case is 1 meter. Now, you're supposed to be finding the velocity too when it swings downwards. Be aware, the center of mass just drops 30 centimeters. So your gravitational potential energy is mgh, where h is 0.3, because its center of mass is 30 centimeters above its lowest point. So you have to adjust both the center of mass and the change in height of the center of mass for this to work out. I want you to imagine that the more you move the pivot point over here, the actual slower the system's going to go. It's easier to turn, but there's less and less torque, and therefore less and less energy. If you mount it at its center, will it even swing down at all? Well, your silence is telling me a lot. But if you mount it at the center of the meter stick, is there any reason for it to change position? No. So I would expect that as it gets closer and closer to the center, it's going to have less and less incentive to turn. All right.